Chapter 6.1. So we're on a new section here, and we're shifting gears, big time shifting gears, because we're getting into the what's called the fundamental identities, which is going to lead into my favorite thing that we do all year in here, which is trig proofs. I love me some trig proofs. Did y'all ever do geometry proofs in geometry, where you start with a lemma or a postulate, and then you have to prove through a series of equivalent logical ideas and some other theorems that justify it to get from point A to point C by going through points B.
Like, why is this circle a circle?
Right, exactly. Why? Yeah, prove that this circle is a circle.
Circle.
Yeah, okay. We're leading there, okay? So let's talk about types of equations real quickly. I know you've already read this. We have name equations. I lost my notes. Hang on. We got name equations, which basically just give a name to a mathematical expression like f of x or g of x or even y equals. That's the name of the function. The name of the function is f. Okay. The of x is the independent variable. The name is f. Okay. We have conditional equations, which are ones like this. These are the ones to be solved. They're only true under certain conditions. We have what's called a contradiction. The simplest contradiction is 1 equals negative 1. That's an equation, right? Is it true though? No, no, that's not true. So we call that a contradiction. We show a contradiction by two arrows that ram heads like that. Okay, think of two rams hitting each other in the wilderness. I don't think so, right? Boom. Does 1 equal negative 1? I don't think so, right? Bless you. Okay, and then we got the opposite of a contradiction, which is an identity. It's something that's true for all values of x. So in other words, 1 equals 1 squared. Is that an identity? Is that always true? That's always true. That's an identity. That's what we call a trivial identity. Here's some that are not trivial. The absolute value of x is the same as the square root of x squared. This is actually an identity that we use quite a bit in calculus because it allows us to use what's called a power rule to take the derivative or even integrate possibly if we want the absolute value of x function. Um, so this whole section is going to be talking about identities. Some trigonometric identities specifically. These are equations that are mathematical replacements with each other's. Now, I'm telling you before we start, number one, you have to memorize your identities. Some people make flashcards, some people go to Quizlet, but you have to know them like the back of your hand. Okay? It's not just looking at a table and saying, I have these choices that I can substitute one for the other. And that's the benefit of that identity, by the way. They're mathematical synonyms, so you can substitute one for the other. But you have to memorize them so that you know they even exist. You have to know that it's even a possibility that you can use these to substitute one for the other. Now, the good news is you already know most of these fundamental identities because we've been using them to evaluate angles from the unit circle, right? The first set of the reciprocal identities. What's the reciprocal of sine? Cosecant. And what's the reciprocal of cosecant? Sine. They are each other's reciprocal, right? So if we state that formally, we would say sine of theta equals 1 over cosecant of theta. That's how we would state it. Sine of theta is 1 over cosecant of theta. Or we could say cosecant of theta is 1 over sine of theta. And this is actually what we would use if we were trying to evaluate something on the calculator like cosecant of pi sevenths. We would type it in as 1 over sine of pi sevenths, okay? So these are your reciprocal identities, which means that you can substitute one for the other. If you ever see 1 over cosecant of theta, you can substitute it with sine. If you ever see cosecant of theta, you can substitute it with 1 over sine. Got it? All right, now we got the next set of reciprocal identities. What's the reciprocal of cosine? Oh my gosh. Secant. Cosine's 1 over secant. So guess what secant is in terms of cosine? 1 over cosine. They are each other's reciprocals, okay? These are identities. You can replace one with the other. What's the reciprocal of tangent? Cotangent. So tangent's 1 over cotangent, and cotangent's 1 over tangent. Got it? All right. So once you have these fundamental identities and you know they're true, you can start manipulating them algebraically. For instance, if I take this identity here and I simply multiply both sides by cosecant of theta, look what happens if I multiply both sides by cosecant of theta. I get cosecant of theta times sine of theta equals, these divide out, and I'm left with 1. Guess what I just created? I created a new identity. Cosecant times sine is the same thing as 1. What's another name for 1? Cosecant times sine, or sine times cosecant, either one. Do you want to memorize that one too? No. So here's what we're going to do. We're going to memorize the fundamental identities. Sine is 1 over cosecant, cosecant is 1 over sine. And then just, if we need to get somewhere else, like if I needed to get to this step here, instead of flat out memorizing it, I'll just say, hey, I'll just do a little bit of algebraic manipulation to my true statement above, and I get another true statement. Now this should make sense to you, because what's 5 times the 5th? 1. What's the 7th times 7? What's 1 over pi times pi? 1. What's anything times its reciprocal? 1. So because cosecant and sine are reciprocals, their product is 1. Yeah. All right. Example 1. Using the definitions of the trig functions in terms of x, y, and r, prove that tangent is 1 over cotangent. Okay, so I'm going to introduce you to the idea of proof. We know that this is true. We've been using this, but how do you prove to someone mathematically that it's true? Proof is a very, very, very tough thing mathematically, right? Outside of a math class, if you were to prove to something to somebody, you might just show them that it exists, right? Hey, look, is it raining outside? Yes, I have rain in my hand. You see it? I caught this rain outside. It's in my hand. You see the rain in my hand? I got it from outside where it's raining, so it must be raining outside. Oh, I believe you. It must be raining outside. You have rain in your hand. Seeing is believing. In math, it's not that simple. That's called verification in math. When you use a specific example, here's the thing in math though, you can't verify something and call it a proof. In other words, if I plugged in an angle from the unit circle here, and I got a true statement on the left and a true statement on the right, that's not a proof. That's just called verifying it for that number. To prove something, you have to use variables. That's the first thing. To prove, you must use variables, not numbers. Okay? Because you got to show that it's true for all values. You got to show that it's true for all values. So here's what you're going to do. Number 1, you're going to draw a line down the middle. Draw a line down the middle. That's the first thing we're going to do, okay? So I'm going to draw a line down the middle. Okay? Number 2, you're going to start with the more complicated side. The reason being is because it's easier to tear down than to build up. Would you agree? Think about just a house. To tear down a house, all you need is a sledgehammer and a lot of willpower, right? You just start swinging. You can wreck that home pretty easily. But or a wrecking ball. Just imagine a giant excavator wiping out a house with one swipe. It's gone. But to build that house, man, you need plans. You need skilled labor. You need it to happen in the right sequence. There's a lot that goes into building something up. Something that wasn't there previously, you have to know what to introduce to erect it, right? To construct it. But to tear it down, you're just using what's there and you're getting rid of it. Okay? Now, here's the idea behind it. You're going to manipulate each side independently. You're going to manipulate each side independently until they match. Okay? And then you're done. Now, when we manipulate it, what are our options when we manipulate it? Well, we have algebra on our side. We can manipulate it algebraically, or we can use identities to substitute something with what it's equal to. Okay? So let's come over here. I can't multiply both sides by cotangent. I can only do that once I prove that it's an identity. To show that it's an identity, I got to work with each side independently and show that the two sides are exactly the same. So I drew the line down the middle. Now the next side is to start on which side? Which side looks more complicated?
Right side.
The right side looks more complicated because it has a fraction. Okay, so here's what I'm going to do. I'm going to replace cotangent with the definition of cotangent in terms of x, y, and r. What?
Or X over Y.
Cotangent is x over y. Okay? And now I'm going to write off to the side definition of cotangent of theta. Remember in geometry you had to like say theorem 2.1 or parallel postulate theorem. There always had to be a reason for what you're doing. All right? Now I've created a complex fraction. How do I eradicate a complex fraction? I stay, change, and do what? Flip. This is just going to be complex fraction. That would be the reason. Or you could say division algorithm if you want to say something like that. Okay? Now I have that times 1. What's anything times 1? No, itself. So this is going to be identity element of multiplication. That's the reason. 1 is the identity element of multiplication because anything times 1 is itself. Now, y over x is another trig ratio. Which trig ratio is it? Tangent of theta. So this reason would be the definition of tangent. Now look at the left side and the right side. Are they the same except for the color difference?
Yeah.
Does tangent of theta on the left equal tangent of theta on the right now? Yes, so the proof is done. So all you have to do when you're done is in the bottom right-hand corner, you write QED. QED. And you don't even need to put dots. It's a stylized acronym. Does anyone know what QED stands for?
You told us before. Like quintessential erratic.
Quintessential.
I remember you telling us.
It was close. I mean, you got the quid part right. Quid. It's quid erat demonstratum. It's Latin for that which has been demonstrated, which is a fancy way that Dora used to end every show with, right? We did it. We did it. We did it. Yeah, lo hicimos. Okay. We did it. That's what that means. Now, if you don't want to put QED because it's kind of stodgy, I encourage you to do something else, right? You could sign your name next to it, like a work of art. I'll be fine with that. If you just want to put something like Shazam or sign off with some type of, interjection, that would be fine.
Booyah.
Booyah is fine. Yeah. So get clever, get creative. It takes the boring stodginess out of doing a proof. But if you ever look at a proof in a textbook, you'll see QED at the end. Okay. Sometimes instead of QED, they just put a little box, which is a little square, a little box, which means we're done. But I would tell you just to sign off with your name. Okay, so there you go. So now we've proven it. So now we know that tangent of theta equals 1 over cotangent of theta for all values of theta in the domain. How do we know it works for all values of theta? Because we used what all the way through? Not numbers, but what? Variables. Okay. Now, when we're proving the fundamental identities, we're going to have to go back to the definitions of the trig functions. But once we get the fundamental identities under our belt, we're going to be able to use those fundamental identities themselves to prove bigger and better things. We're not going to have to go back to the definition in terms of x, y, and r. Got it? Yeah. Has it been 15 minutes?
Yes.
Okay, it's all yours. All right. Let's look at the next set of identities, which guess what? You already know. We're just giving a name to them. We got the reciprocal identities, and now we have the quotient identities, or I like to call them the ratio identities because they are ratios. All right, what is tangent? Tangent's y over x, but that's the same as what? Sine over cosine, because on the unit circle isn't sine y, and x is cosine? So if tangent's y over x, and y is sine, and x is cosine, then tangent is sine over cosine. All right, what's another name for tangent in terms of sine and cosine? Sine over cosine. And what's another name for sine over cosine in terms of tangent? Tangent. So if you ever see sine over cosine, you can replace it with tangent. Or if you ever see tangent, you can replace it with sine over cosine. They mean the exact same thing. All right, now, what's another name for cotangent? It's cosine over sine. Do you already know these two identities? Say yes. Yes. Yes, you do. Yes, you do. So this is nothing new. We're just now formalizing that they are, in fact, identities, and we're giving that family of identities a name. We have the reciprocal identities, and we have the ratio identities. Okay? It's a ratio of two trig functions. Now, here's what's cool about the reciprocal and ratio identities, because they not only work for single powers of trig functions, but they work for multiple powers. So, for instance, what is the reciprocal of 1 over cosecant squared? Sine squared, because that's really 1 over cosecant times 1 over cosecant, which is sine times sine, which is sine squared. What's another name for tangent to the fifth of theta in terms of sine and cosine? It could be, yeah, it could be 1 over cotangent to the fifth. Very good. There's two things, right? 1 over cotangent to the fifth, or sine to the fifth over cosine to the fifth. Now, let's talk about what Brady just did. This is one of the reasons you need to have your identities memorized. Because if you're staring at tangent to the fifth power, you need to know what your options are. Your options are 1 over cotangent to the fifth of theta, or sine to the fifth over cosine to the fifth. Which one? Is that Ryan? Yeah. How do you know which one to use? Well, it depends what you're trying to accomplish, right? It depends where you're trying to go. If you're not sure, you try them both out. But knowing that you have two options and knowing one of them is in terms of sine and cosine and the other one's in terms of cotangent allows you to correctly use the one that you want when you're moving from point A to point C by way of point B. Got it? All right. Now let's go ahead and prove cotangent equals cosine over sine. Let's prove it. First step of the proof is to draw a line down the middle. That's going to keep you from cross-contaminating both sides. I can't multiply both sides by sine. I can't add 1 to both sides. I have to work each expression independently. All right, now that I've drawn the line, I pick the side to start on. Which side has more information, the left or the right? The right. The right has a quotient. The left is a single trig function. So here's what we're going to do. We're going to go ahead and use the definition of cosine and sine. Cosine is x over r all over the definition of sine, which is y over r. What would the reason be? Definition of cosine and sine. Now guess what? Just like before, I've created a complex fraction. So state change flip, x over r times r over y. And that would be complex fraction. Now we look to do some algebra. Is there anything happening here algebraically? The r's divide out. So I'm left with x over y, and we'll just say division. Division of r's. They divide out. And I'm left with x over y. Is x over y a known trig function? It's which one? Cotangent of theta. So the reason would be definition of cotangent. Now look at the left side and the right side. Are they the same? They're the same. So now we sign off with QED or something else of our choosing. So long as it's clean. Don't put like F yeah and write out unless it's factor yeah. Factor yeah. Yeah. Keep it clean. Now you can use something different every time and get creative, or you can come up with your own personal stamp that you use every time, like booyah, or what Emeril Lagasse always said, kick it up a notch. Let's kick it up a notch. Stuart Scott always said booyah. Awesome sauce. That's a good one. Awesome sauce. Dirty diapers. That's another good one. No, don't put dirty diapers. That's gross. Okay. All right, now we're getting to our set of first new ones. These are the first set that you have not seen before. These are called the Pythagorean identities, or as I like to call them, the PIDs for short. PID, Pythagorean identities. Got them? These are the PIDs, which is short for the Pythagorean identities. Now, the Pythagorean identities say that x squared plus y squared equals r squared, right? That's the Pythagorean theorem. What is x on the unit circle, though? On the unit circle, isn't the x coordinate the cosine? Yeah? And the y-coordinate, isn't the y-coordinate sine? And on the unit circle, what's the radius on the unit circle? 1. So your first Pythagorean identity is basically x squared plus y squared equals r squared from the unit circle. It's cosine squared plus sine squared equals 1. That's an identity, okay? So what's another name for cosine squared plus sine squared? 1. What's another name for sine squared plus cosine squared? That's commutative, right? It works the same way. Sine squared plus cosine squared or cosine squared plus 1. So if you are ever staring at cosine squared plus sine squared, you can simplify it by just calling it what? 1. If you're ever staring at the number 1 and you want to kick it up a notch, you could call it what? Cosine squared plus sine squared. All right? Now this guy I call Papa Pid. You're going to get used to me calling it Papa Pid. The reason he's called Papa Pid is because it's alliterative, but he's also the primary pid. The other two Pythagorean identities can be spawned asexually, if you will, from this single parent. Okay? Just like, yeah, budding. I think in biology they call that budding. It buds off and then it splits and becomes its own thing. How do we get the first baby pid then? Well, the first baby pid comes from if we divide everything through by cosine squared of x. Divide everything through by cosine squared of x. Okay, we could do that. Once it's an identity, we're allowed to manipulate it algebraically. If we're proving that it's an identity, then we got to work each side separately. All right, what's cosine squared divided by cosine squared? Ryan, are you off your phone still? Cosine squared divided by cos squared is 1. What's sine squared divided by cosine squared? Tangent squared. And what's 1 over cosine squared by the reciprocal identity? Yeah, secant squared. The reciprocal of cosine secant, right? So notice we use the ratio identity on the second term, and we use the reciprocal identity on the third term. Guess what baby pid number 1 is? 1 plus tangent squared of x equals secant squared of x. There's your baby pid number 1. Baby pid number 1. Baby pid number 1. He comes from Papa Pid, asexually. Asexual reproduction. All right. You got to memorize that. These are new. You think you can memorize that? What's another name for 1 plus tangent squared? What's another name for 1 plus tangent squared? Secant squared. What's another name for secant squared? 1 plus tangent squared. What's another name for cosine squared plus sine squared? 1. Got it? Okay, now I'm going to get rid of all this algebraic mess because I'm going to show you how to spawn baby pid number 2. Baby pid number 2. Instead of dividing everything through by cosine squared, baby pid number 2 is like a fraternal twin. We divide everything through now by sine squared. What's cosine squared over sine squared by the ratio identity? Cosine over sine. Come on, people. That's cotangent squared. Plus, what's sine squared over sine squared? That's easy. That's what? 1. And what's 1 over sine squared by the reciprocal identity? Cosecant squared. Good. Now, cotangent squared plus 1, that's the same as 1 plus cotangent squared, isn't it? So I put it in that form because it's easier to remember. Here's baby pid number 2. What's another name for 1 plus cotangent squared? Cosecant squared. What's another name for cosecant squared? 1 plus cotangent squared. Now, here's why I put them in the same form. Notice they both start with 1, don't they? It puts them in the same form. If you memorize baby pid number 1, 1 plus tangent squared is secant squared, baby pid number 2 comes for free. It's its fraternal twin. All you got to do is add what to the two trig functions? The word co. So 1 plus cotangent squared equals cosecant squared. You got it? Or if you memorize baby pid number 2 instead, to get baby pid number 1, you just drop the cos. 1 plus tangent squared is secant squared. You got it? So you shouldn't have to do the math every time and spawn these babies from scratch asexually every time. You should memorize both of them, or I still to this day, after 25 years of teaching it, I still memorize baby pid number one, and if I need the other one, I just quickly in my head add co's in front of it.
So are they like inversions or reciprocals?
What's that?
Are the two baby pigs reciprocals?
No, the two baby pids are not reciprocals. No, because you can't secant and cosecant are first of all are not reciprocals of each other. And because this is two terms, if you flip that, you get 1 over 1 plus tangent, which it doesn't work. So no, they're not reciprocals of each other. They're not reciprocals of each other. They're not even cofunctions of each other. Okay? It's just a convenient way to help you remember one from the other. Okay? All right, now, unless you're trying to prove it, you can actually manipulate it on both sides. So watch this. I can actually subtract tangent squared from both sides and get 1 equals secant squared of x minus tangent squared of x. That's another identity. Do you want to memorize that identity? What's another name for 1? Cosine squared plus sine squared. True. But what's another name for 1 in terms of secant and tangent? Secant squared minus tangent squared. Woohoo! Do you want to memorize this new identity here? The answer is no. Don't memorize it. Just memorize baby pid number 1. And if you need to subtract tangent squared from both sides algebraically, go for it. Okay? So far we've learned 3 sets of identities. The reciprocal and the ratio, which you already knew coming in. Would you agree? And now the new ones, which I'm having you memorize 2 of them. Papa Pid for sure. And as long as you memorize baby pid number 1, baby pid number 2 comes for free. Okay, let's go ahead and review this. If I write cosine squared like this is the condensed way to represent cosine quantity squared. It's the same as cosine of x quantity squared. So when we're working with the quantities, if we're evaluating the quantities, we want to write it in this expanded form. But whenever we're writing it as a presentation or we're just manipulating it, cosine squared is the condensed form. It's easier to work with. All right. Last thing for the day. I think that'll be good for Friday. Using the definitions of the trig functions in terms of x, y, and r, prove Papa Pid. Let's prove Papa Pid. Are you ready to prove Papa Pid? You draw a line down the middle. Now you pick the side to start on. Which side's more complicated, the left or the right? The left. Okay. Now the first thing that I'm going to do is I'm going to write cosine squared of x is cosine x squared plus sine of x squared. What would be the reason? The reason would be notation. All right. Now what am I going to do? I'm going to replace cosine of x with its definition in terms of x, y, and r. What's cosine? X over r. What's sine? Y over r. This would be definition of cosine theta, sine theta, or cosine x, sine x, whatever. All right, now I have a quotient squared. That's the same as x squared over r squared plus y squared over r squared. And this is just exponent rule. That's just the rule of exponents. When you have a quotient raised to a power, both the top and the bottom get the power. All right, now I have 2 terms. I'm trying to show that it equals 1. What do I need in order to combine fractions? A common denominator. Do I already have a common denominator? I do, so I could add the numerators together. X squared plus y squared all over the denominator. This is just add fractions. That's the reason. And now I get to x squared plus y squared over r squared. Hey, what's another name for x squared plus y squared? What's that? It's the Pythagorean theorem. What's x squared plus y squared equal to on the unit circle? No. No. R squared. I gave it to you up here. That's the same thing as a squared plus b squared equals c squared, except this is the unit circle version. What's x squared plus y squared? It equals what? R squared. Yeah, so what? Look, everybody. I can replace x squared plus y squared with r squared. This is the Pythagorean theorem, which is where the identities get their name. And now what's r squared divided by r squared? 1, that's division. Does the left side look like the right side? Yes, so now I'm going to sign off with a bad word. Heck yeah. Sorry, that's a little strong, right? Heck yeah. Dirty diapers. Actually, I like dirty diapers better. Dirty diapers. Oh, yeah. So now we know Papa Pid works, right? Does Papa Pid work? Yeah, it works for all values in the domain, which for sine and cosine is all real numbers. Okay? Your charge for the weekend, before we get into more identities, is to make sure you thoroughly understand and have memorized those three sets of identities. The reciprocal and the ratio, you already know. You just need to get used to them, especially when they have higher powers on them. And you need to memorize the three Pythagorean identities, okay? Over the weekend, you think you can memorize those three things right there? Say yes, heck yes. Okay, we're done for the day. Any comments or questions? Okay. Thank y'all for being captive audience on a Friday morning.